of the possible functions that connect this place, x1 and y1, with this place, x2 and y2. Okay, so let me draw a couple of choices. You know, here's a function. Here's a function. Here's a function. These are all differentiable functions which connect the points x1 and x2. There are many more of them. I drew only 3. Okay. What you'll notice is that they all have the following in common. Delta y between these functions is this bit here. Delta y is the difference between the functions. Delta y is 0 by design at x1 and 0 by design at x2. Therefore, this term, which came in my integration by parts, is 0. Because delta y is 0 at that limit and 0 at that limit. Does this make sense? This is an important step. You integrate by parts, you get rid of the boundary term. This is called the surface term or the boundary term, and your goal is to arrange things so that this term goes away. Almost always you want this term to go away. Yeah?
But then, I remember you saying that, but then for the other term, delta y is not 0.
What's that? Right, so it's not 0 inside. It's 0 at the edge, but it's not 0 inside.
Even though for the other term, there's still an integration between x.
Yeah, so I still got that other term, right? So I'm not saying that the product of delta y and this derivative of stuff, when I integrate it over the thing, isn't going to be 0. It's just at the boundaries, delta y is 0. Okay, so if I go, so I have this term up here, right, which has become these two terms right down here, and I put all that back together. I have the variation in j is the integral from x1 to x2. Derivative of f with respect to y, delta y, minus d by dx of the derivative of f with respect to y prime, multiplied by delta y, dx. And so now I can factor out that term. Okay? So when I integrate by parts, the result of doing that is that I can factor my delta y out back because it's not being, a derivative isn't being taken of it anymore. And now I have this quantity in parentheses. Alright? Delta y is not 0 everywhere in between. Alright? So if you have an integral of this type, then what must be true, if this is going to be true for all delta y, is that this thing has got to be equal to 0. So So if delta of j is going to be 0 for any possible variation in any possible set of functions, what has to happen, the logical steps that lead you to state this, is that this quantity that you've integrated has got to be 0. And that last step there is that if this is going to be true for any possible function y, then this has got to be true, that the quantity in parentheses has to be 0. And this is the Euler Lagrange equation. Now, let us look at what it says. It says f is whatever f is. I take f's derivative with respect to y, and then I take the total derivative of the derivative of f with respect to y prime. I set that equal to 0. All right, now f depended on y and y prime. Okay? So there were first derivatives in f, in the y primes. When I take another d by dx here, I get second derivatives of y. Okay. So if I tell you what f is, and then you do this equation to it, what you get is a second order ordinary differential equation for y. Let's write that down. Given f of y prime. All right. So, yeah.
Real quick, when you in the Euler Lagrange equation, you didn't include the variance in y because the difference between those functions is 0 all the time.
That's right.
So you know, okay.
Yeah. So since delta y is going to be 0 all the time, and I want to think about any function that I might possibly think of, then this thing in parentheses has got to be equal to 0, and that gives me the Euler Lagrange equation. All right. Let's go through this. All right. J is the integral of f. I want to find f's arguments are functions y of x. My goal is to find the function y of x that makes j extremely. So I take the variation of j and set it equal to 0. Taking the variation of j and setting it equal to 0 and doing a little bit of differential calculus gives me this equation called the Euler Lagrange equation. So a function y satisfies the Euler Lagrange equation. Okay? So given your f, you plug f into the Euler Lagrange equation, and that gives you a differential equation for y. You know, y prime plus y double prime over 2 is equal to 0. Whatever it is. Okay? When you solve that differential equation, you get a function y of x. Which function y of x do you get? You get the very function y of x that makes j extremely. So the Euler Lagrange equation is a prescription for finding the function which makes j extremely. Got this? So I said up at the top of the class, we want to find a rule or a way to pick the function which makes j have a minimum or maximum value. The rule is the Euler Lagrange equation. Okay? When you apply the Euler Lagrange equation, I like to say apply the Euler Lagrange equation, because when you apply the Euler Lagrange equation, you get a differential equation out. When you solve that differential equation, you get a function. The function you get is the function which makes j extreme. Within the boundary of x1 and x, between these initial places that you remember. Okay? So, examples. Let's suppose that you ask yourself this question. I'm going to throw this simple object through the air. There are many paths, y of x, that the object could choose. When I let go of it, it could choose to go up, and it could go like this, and it could come back down. It could choose to go down and then come back up and come over here. But nature picks one path. Nature picks one y of x. The one that it picks extremizes a particular j interval that we will write down. Yeah.
When we extremize that path, if you're looking at minimum distance, it would just be a straight line, point A to point B.
But it's not.
But it's not. So then what are we actually minimizing in the path? Is it a combination of
action.
Time?
And Professor Devaney would be so excited that I just said that.
Yeah, because the function y would depend on also the initial velocity and the gravitational force, which is derivative.
That's the key. It depends on the gravitational potential in this room. If I do that in space, I say, which path would nature take in space for me when I release the object I want it to get here? It would take a different path than if I asked which path will it take in the room.
If there was no gravity,
If there was no gravity, right? If there was no gravity in space, it would go.
it would just go
That would be
straight
the
through.
path it would take.
So this is like the underlying proof that people are
It is one way of looking at it, is this what we're going to do is, one aspect of what we're going to do is it's the underlying proof of F equals MA. Right, so here's another one, right? Let's suppose that, so these are some of the homework problems. Let's suppose that you have a surface like a can, cone, a cylinder, a hill, and you're going to start at this spot here, and you're going to end up at that spot there. There are many ways to travel along the cone and get from here to there. One of them is the shortest. Which one is that? Is it shortest to go over and then straight up? Is it shortest to wind around a bunch of times? Okay. Here's another one. Light is going to flow through the air and then run into a piece of glass which has some index of refraction that maybe is varying with space, and come out the other side. Of all the, the light's emitted here, and the light gets to there. Of all of the possible ways the light could go through the glass, it picks one. It picks the one that is generated by Snell's law. Go to Snell's law, physics 244. That's all, sorry. Damn, the camera wasn't pointing at Turk at that point. That would never thought. So, if you write down an integral which says how long does it take the light to travel from this point to that point, and you find the path that takes the least travel time, you pick the path that the light travels. So the integral becomes how much time does it take the light to get from here to there? And the minimization of that time is Fermat's principle. The light takes the path that takes the least amount of time. Okay? So you can get Newton's laws out of this, you can get the geodesics on a surface. Geodesics means the shortest path distance. You can get Fermat's principle out of this, that light takes the path that takes the shortest amount of time. This is like, and then, you know, once you do this, then the quantum field and quantum field theory takes the path of least time. You write down action integral in quantum field theory, then you apply this and out it plops what the quantum fields do.
QED, they take all the paths.
And QED, you take the sum of all the possible. I mean, so it's just, oh, this idea goes over and over and over again throughout the rest of physics.
So that equation shows us a function y that'll that'll pretty much minimize the amount of energy or whatever, like driving
Whatever the
force
J is.
acting.
Yep.
And
Yep. So the idea is that J is some integral that for some physical reason we think should be minimized in this case. Maybe it's the length, maybe it's the travel time, maybe it's some other function thing. The Euler Lagrange equation gives us a differential equation that when we solve the differential equation, we get the function which minimizes J. And when I say minimizes, it technically extremizes J, because in some cases it usually picks out the minimum, but it doesn't always pick out the minimum. For example, in gravitational lensing theory, you get multiple light rays that go from the source to the observer. They go around the lens in different ways. Some of those paths are the locally shortest time to get from here to there. In other words, if you went a slightly different way, it would take you longer. But one of those paths, so if you had 3 images, 2 of them would be the locally shortest time. The third one would be the locally most time. So if you took any path other than that path that was slightly off from that path, you would get a time that was less than that path. And so the 3 paths that you get are 2 minimums and 1 maximum. And so this idea is that it's really the local extrema. Might be a minimum, might be a maximum, frequently is a minimum. If there's only one, it's almost always a minimum.
why would it take a maximum?
Well, Fermat's principle says it takes the extremal path. Nature works that way. It's a funny thing. Alright. So I wrote us 2 class activities and a homework set. Item A is more on gravitational potentials. I'd like us to do item A first for at least 35-40 minutes. If we don't finish item A in 35-40 minutes, I want you to work on it on your own. Okay? Then item B starts down the road of making sure we understand all the stuff that we just said. Okay? That sort of makes sense? Alright, let's look at item A real quick. Item A is a generalization of exam problem 5. There's a bar. This is at x equals 0. This is minus L over 2. This is plus L over 2. And here is the point x, y. So it says, compute the gravitational potential at the point x, y, a general field point. So not at the middle, not at the end, not someplace else, just some general field point. So the potential phi is minus g the integral dm over r. Now, this threw people for more of a loop than I expected it to. It's a bar.
Cylinder?
It's not a fancy cylinder. It's not a sphere. It's a line.
It's a Y.
I don't think anybody thought it was a sphere. Lots of people tried to do cylinder things. Lots of people did things that had area elements. Lots of people did all sorts of crazy shit. So dm is lambda dx prime. Here's r. Here's x prime. Okay. You can lambda here means mass per unit length, so that's just m over l. You can always write r as x minus x prime squared plus y minus y prime squared plus z minus z prime squared. You can always write r that way. Where is the bar?
It's along the x-axis.
It's on the x-axis, which means y prime is equal to
0.
0. And the bar is located between x prime equals minus L over 2 and x prime equals plus L over 2. Does that make sense? Okay. Alright, so you can set y prime equal to 0. And these guys here become your integration limits. So you might want to get out your test where it tells you how to do this interval. Alright, so that gets you started, right? So, compute the potential, evaluate the potential at x equals 0. That would have been the first half of the test problem. Find the gravitational field by taking the gradient. If you got the potential, it's a function of x and y, you can take its gradient. Tells you the field. Tells you g. If you don't do it at a general point and you try to take the gradient, you can't get the x component. These aren't any x's. If you evaluate this at x equals 0, before you take the x derivative, you can't get anywhere. Okay. So that's 1, 2, 3. 4 is to go get the gravitational potential by doing an integral. 5 is cute. 5 says take the limit as L is much greater than y. In other words, if you're really close to this thing. If you're really close to it, what does it look like? What does this look like if you're a really tiny, tiny microscopic bug?
Infinitely long.
It looks like an infinite line. So in 6, it says compute the gravitational field of an infinitely long bar with mass per unit length lambda equal to that of r bar, and see that you get the same result as 5. That's a clever example.
Wait.
So you can use Gauss's law on an infinitely long line of mass. You should get the same result as if you take the gravitational field that we compute in 4, and then take the limit that you're really, really close to it. Okay? People kind of okay? Sort of know where you're going to go? Alright, start working. I'll come around and talk to you.